Hey everybody, Dr. J. Let's get straight into it. Vaporization and condensation. Okay, vaporization is basically all we've been talking about this whole unit is states of matter. We talked about states of matter, and we've been talking, more in detail, adding that layer on top of them. So we talked about solids, liquids, and gases, right? Check out the previous videos if you want more information. But now let's talk about these processes as far as transforming, right, from one state of a matter to another. So let's start with a basic one, vaporization, right? Evaporation, okay? We probably heard these terms before. This is where we have our liquid state of matter and it's going to evaporate to form our gas. Okay, that's as simple as it gets, right? We see this commonly with, boiling water, anything, right? You put the liquid on, the steams up, it's going to turn to gas. It's just in a natural process of life. The next one that I want to focus on is condensation. Okay, so condensation, if you didn't know this one is when you have gas molecules, those particles, right? And they're being condensed down to form our liquid matter. Okay, so we're just going to focus on these two processes. Okay, we're going to talk about these, but once again, we're going to just add a little bit later, okay, because we know the basics. We know what vaporization is, liquid to gas, condensation to gas to liquid, but let's talk about them. Let's talk about this. So let's look at this graph here. On the y-axis, you got the fraction of molecules. So just think of these are our molecules or particles going on here. Then on the x-axis, we got our kinetic energy, okay, so this is our overall energy, our motion of energy that we need, right? So our molecules y, okay, so basically we go up, right, we're increasing the amount of molecules, and if we go towards the right, we're going to need more energy, okay? So we just want to understand what we have here on our axes, okay? All right, so the blue one is my low temperature, and then I got my higher temperature. Here's the most important part of this entire graph is our energy, okay, and we'll get more into this later on with the semester, but this process of vaporization is from liquid to gas. So right now, these are just, think of these as liquid molecules, okay, and we see that all this section is just liquid molecules, but we need a certain amount of energy, right, to have that actual conversion from liquid to gas, and this certain amount of energy is a minimum kinetic energy that we need here. So we can see that for this example, it's going to be right here in the graph. Okay, and basically everything else after this minimum, okay, is gas particles. So what's happening here, right, is what we can see right during this entire process, right, only a little amount of particles are being able to basically be transformed into gas particles. Okay, only a small amount right here. So we look at lower temperature, right? If we got that low temperature example, we can see that at this point, right, that's the point that we reached, that the minimal kinetic energy needed for it to convert. So at this point, at the lower energy, we're only getting this small portion of our gas molecules now, right? This is it at the lower temperature. But let's say, right, if we increase that temperature, we're going to see a couple different things, right? Notice, as soon as we have a higher temperature, say we're at 100 degrees now, 100 degrees Celsius. Notice, right, the amount of liquid molecules we have is lower now. Okay, so we see this, right? Now that higher temperature, less amount of liquid. Okay, so there's a couple reasons why, right? Higher temperature, this means that now, right, those molecules we know are moving around doing their whole thing, right? So now this is going to increase our evaporation of our liquid molecules all over here. And remember, this is the minimum amount that we need right here. That's the minimum amount. So once we hit that point with the minimum amount, guess what we see at higher temperatures? There's more gas particles that are escaping, right? Forming once we meet the amount. And that's all because of us having this higher temperature, okay? So vapor pressure depends on intermolecular forces, okay? I'm going to talk about two types of liquids. I'm going to talk about volatile liquids and non-volatile. So basically, when I'm saying volatile liquids, okay, I'm talking about ones that are going to have high vapor pressure. They have high vapor pressure. So if you have high vapor pressure, that's basically meaning that you're able to be evaporated quickly, right? You're going from liquid to gas pretty quick. Good example of this is like butane. Butane can quickly, if you ever worked with butane before, right, or butane lighters, right, it can be converted to gas very quickly, right? If you even leave it out for an extended period of time, it's going to evaporate on its own without having to heat up or do anything like that. A reason why, right, butane will have a high vapor pressure, has a small molecular weight, or it has a small or weak, right, intermolecular forces. So weak forces basically can impact your vapor pressure. Okay, so we're not going to see, usually volatile liquids aren't really going to have too many hydrogen bonding or dipole-dipole intermolecular forces happening going on there. Okay, non-volatile, totally the opposite, right? So we're talking about liquids that are not going to evaporate as fast. So because of this, they have low vapor pressure. And here are 2 points when we're talking about non-volatile liquids. Instance, right? If you look, it's totally the opposite. Small is volatile, large molecular weight will be non-volatile. So the bigger the weight, right? So for instance, if we're looking at some type of oil, okay, this is going to have a low vapor pressure. You ever spilled oil before, right? You can come back to it 3 days later. It's probably still going to be there as a liquid. It's not going to disappear. For instance, if we spill butane or something like that. So yeah, this is a huge thing. The larger the molecular weight, as well as the intermolecular force. So for instance, if you have a bunch of London forces, like the bigger the molecule, the more London forces it has. This can also be a very impactful thing. As well as second point here is large intermolecular forces. So when I'm saying large, I'm just talking about stronger intermolecular forces. So the stronger that intermolecular force, right, you're going to see a low vapor pressure. For instance, like water. Okay, water has hydrogen bonding occurring going on. So because of this, okay, water is not going to have a high vapor pressure compared to like butane, right? Just based on comparing those intermolecular forces, okay, in that light, right? So these are the 2 things that are going to impact whether you have high vapor pressure or low vapor pressure. Look at the molecular weight and look at the intermolecular force. This is basically a barometer. We're looking at basically the pressure, right? And we got our atmosphere. So this is just our standard. This is a standard atmosphere. And for instance, let's compare 3 different types of liquids here. We got water, we got some ethanol going on here, and then we got this ether, right, with this 2 carbon chains over here, 2 carbons, okay. We look at our water here, right? We just said that the standard pressure is 760 torr. So we look at the difference here. This water is giving off a certain pressure. Okay, in this case, all we have to do is really subtract. So that's what we're going to do here. It gives a certain pressure with the barometers. Okay, so basically we're going to see that it's going to be 24 torr. 24 torr. We go to ethanol. I'm just going to cover what was happening here so we understand what happened there. We're going to be at 65 torr. And then if we go to 545 torr. Okay, so we can see, right, one has a higher pressure and one has a lower pressure. Now, let's talk about this. Non-volatile liquid. Okay, in this case, just one that has lower vapor pressure. Water. Why do you think, right, that water would be dramatically lower than this one over here? So let me remind everybody that this is diethyl ether, basically, okay? So remember, we got this oxygen in the middle, followed by our 2 carbons on the side, okay? That's all this is. That's all that is. If you see how this written, it can be confusing. That's all it is. It's just say oxygen with 2 carbons coming off of it. Why would that be a huge difference? Okay, if we got this one that has extremely high pressure, so this is telling me that it's going to be very volatile, but this one that is not a high pressure, so it's not as volatile. Just think about it. Think about it. Let me know in the comments what y'all thinking. Let me know in the comments what y'all thinking if y'all got any questions real fast about this stuff. But I'm just going to compare these two. Now, hopefully you guys thought about it. Let's talk about those intermolecular forces, okay? Water. What type of forces we got going on? Hydrogen bonding, right? That oxygen is bound to that hydrogen is bound to oxygen. Anytime you got that going on, right? We got hydrogen bonding. Now let's talk about this one. That was a trick, right? It's a trick. Because we just explained how ether looks, oxygen bound to a carbon. We don't want to get that confused, right? So I highly recommend if you didn't know, right, that this was going to be bound that way, go ahead and review those Lewis structures. It's perfectly okay though. But this oxygen is bound to a carbon, not a hydrogen. So since it's bound to a carbon instead of a hydrogen, this isn't hydrogen bonding, right? Not at all. This is not hydrogen bonding. So because it's not hydrogen bonding, it's not a strong force. Okay, no strong forces there. And because it's not a strong force, right? I don't see it's not any of the higher forces that we talked about before, right? So because of this is a weak intermolecular force occurring here. Hence, this is the reason why this has a high vapor pressure. Okay. So if you guys need me to go over, right, just looking at compounds and understanding how they are bound, let me know in the comments. I could definitely just do a video. Like if you wasn't sure that this was ether, let me know in the comments. I could definitely do a video over that as well.